When we think of unsteady state heat conduction, we consider temperature not only changes with space but also with respect to time. With respect to space, it can be one dimensional, two dimensional, or three dimensional. But today we will see something which is zero dimensional, that is, temperature varies only with respect to time. This corresponding mathematical approach is known as lumped parameter approach. Let's start with an analogy. We have a small island with buses and some boats in the sea. People want to go out from the island to their destination. From the island center, they have to travel to the harbor by bus and from the harbor by boat to their destinations. The overcrowding of people at the island center depends on the boat traffic from the island and the ground transportation system on the island. If there is an excellent ground transportation system with plenty of buses, there will be no overcrowding at the island center. But when the opposite is true, there will be huge overcrowding at the island center, creating a large difference between the population at the harbor and at the island center. Now we consider a similar scenario in a heat treatment process known as quenching. In this process, a heated metal is rapidly cooled by immersing it in any liquid. So in heat transfer, a poor ground transportation system corresponds to poor heat conduction in a body, and overcrowding at the island center to the accumulation of heat and subsequent rise in temperature in its inner body relative to the surface of the body. Like passengers at the harbor, heat changes vehicles at the surface from conduction to convection. The second case you see here shows a good transportation system which corresponds to good heat conduction. So here you can see the temperature gradient is quite smooth and there is less heat at the center of the metal ball. The essence of the lumped parameter analysis is the assumption that the temperature of the solid is spatially uniform at any instant during the transient process of heat conduction. This assumption implies that the temperature gradients within the solid are negligible. According to Fourier's law, heat flux is directly proportional to the negative of the temperature gradient within the solid. So the absence of a temperature gradient implies the existence of infinite thermal conductivity, and no such material is known to exist. Therefore, temperature gradients and thus temperature differences must exist within the body, no matter how small, in order for heat conduction to take place. However, the condition is closely approximated if the resistance to conduction within the solid is small compared with the resistance to heat transfer between the solid and its surroundings. So, under certain conditions, we can study the heat transfer by neglecting the temperature variation within the body, that is, the entire body is at uniform temperature, and consider the body to be a lumped mass. Now let's see the criteria for lumped parameter analysis. What we see here is Biot number, which is given by the formula HLC by Ks, where H is the heat transfer coefficient, LC is the characteristic length, and Ks is the thermal conductivity of the solid. Now if we rearrange it, you can see the numerator shows conduction resistance within the body and the denominator shows the convection resistance at the surface of the body. We need to keep the temperature distribution uniform throughout the body. For this to happen, the conduction resistance within the body should be very small or negligible. So the lumped system analysis is exact when Biot number is equal to 0. But since this is not possible due to a small temperature gradient existing in a body, we can assume that the Biot number to be less than equal to 0.1 for the lumped parameter analysis to be applicable. Now let's move to the formulation. Here you can see a hot steel ball which is at temperature T and its surface is at the temperature Ts and is immersed in a liquid at a temperature T infinity. For this system, we can write the energy balance as E in minus E out plus E generated is equal to change in the energy inside the control volume with time. Since there is no energy in, we can remove E in and it is only losing heat to the surroundings, so we keep minus E out. We are also neglecting the energy generation within the system, so you get the final equation minus E out equal to dEcV by dt. Since the metal ball is losing heat to the surroundings by convection, we can write the left hand side as HAS into the temperature difference between the surface and the ambient air, and the right hand side is actually the internal energy of the control volume, so we can write it as rho Vc dt by dt. Since this is a lumped mass, temperature everywhere inside the ball is same, so we can assume that T surface is the same as the temperature anywhere within the body T. Now we can assume a term theta which is T minus T infinity, and if we differentiate it on both sides we get d theta by dt as dt by dt, because T infinity is a constant. Substituting the value of theta in the energy balance, we get d theta by theta equal to minus ASH by rho Vc into dt. Now if we integrate both sides, we get ln theta is equal to minus ASH by rho Vc into t plus ln of C1, which is a constant. Simplifying it, we get the equation theta is equal to C1 e to the power minus ASH by rho Vc into t. Now if we apply the initial condition at time equal to 0, we see t is equal to ti, then theta will be ti minus t infinity. So after applying the initial boundary condition, we get the final equation as theta is equal to theta I into e to the power minus ASH by rho Vc into t. Now we get a constant term which we can represent by tau as rho Vc by HAS. This is known as thermal time constant. If we rearrange this, we will see this as a product of 1 by HAS into rho Vc. 1 by HAS is actually resistance of the body to convection heat transfer, and Ct is the capacitance or the ability of a body to store thermal energy. This is like RC circuit in electrical circuit theory, so this analogy is from the electrical field. If we look at the terms in the box, it should be non-dimensional, because when we write e to the power something, it should be unitless. So the tau is also having the same unit as time, seconds. Let's see at some observations from this equation. The values of theta and theta I in this equation, we will see it in the numerator as t at time t minus t infinity by t initial minus t infinity. So from this we can say that we can determine the temperature of the body at any time t. Also the time required for the body to reach a specified temperature t. The second observation from this equation is that if a body is at temperature Ti initially, it reaches the ambient temperature exponentially. Let's look at some physical insight of the thermal time constant. If we see in a plot of temperature and time, we will see that for a small thermal time constant, the body reaches the ambient temperature faster. A small time constant means small v by a. V is actually the volume for storage of energy and A is the surface area for losing the energy. If surface area is larger than the volume, then there is rapid heat transfer from the surface as compared to thermal storage. So that means body will quickly adapt to its change. Means if you have small time constant, your body will reach the ambient temperature faster because it will adapt to it faster. If you like this video, kindly like and subscribe and keep watching for more interesting videos.